I'm going through a free masterclass by Eric Bogatin, and I'm sharing what I learn and how I interpret it along the way. These are learning notes, not lessons. Follow along if you're learning too. In this lesson, I'm learning about the frequency domain and why it's such a powerful way to analyze signals. The main value of the frequency domain is that it often makes problems easier and faster to analyze. In the time domain, a signal might be described by thousands of voltage samples over time. In the frequency domain, that same information can sometimes be reduced to just a few key frequency components. We move between these two views using tools like the FFT, which takes us from the time domain into the frequency domain, and the inverse FFT, which brings us back again. Nothing is lost in theory, it's just a different way of looking at the same signal. One important idea here is that in the frequency domain, the only signal that exists is a sine wave. That's because sine waves are the natural response of physical systems. They show up everywhere, even in signals that don't look sinusoidal at all, and they are the solutions to second-order differential equations that describe real electrical systems. This means that any signal we see in the time domain, even something like a square wave, can be represented as a sum of sine waves at different frequencies. That's what Fourier series show us. The square wave isn't made of sharp corners in the frequency domain, it's made of harmonics. This leads to the question, why use the frequency domain at all? Some signals are simply much easier to describe this way. Instead of dealing with thousands of time domain points, we can describe a signal with a few frequency components and their amplitudes. In some cases, thousands of points in the time domain collapse down to a single point in the frequency domain. Each frequency component in the frequency domain appears at multiples of the fundamental frequency. In other words, the frequencies are at n times 1 over t0, where t0 is the period of the signal. There are also practical limits to what we can see in the frequency domain, and these depend on how we sample the signal. The lowest frequency we can resolve is set by the total time window we observe. It's basically 1 divided by the time interval. The highest frequency we can see is limited to half the sampling rate, which is the Nyquist limit. So when we look at a signal sampled over a short time window, we automatically limit the lowest frequency we can detect. And when we sample too slowly, we lose high frequency content. The key takeaway for me is that the frequency domain isn't replacing the time domain, it complements it. Some problems are easier to understand in time, and others become much clearer once we switch to frequency. Learning when to move between these two views is a big part of understanding signal integrity.